All right. So as these fluorine atoms come together and merge, what's going to happen is this fluorine, we're only going to look at the second orbitals, not the first. The 1s we're just going to ignore. Nothing's going to change about it. It's protected. It's underneath these. It's hidden under the covers. Nothing's going to happen to it. There's no monsters under the bed that are going to come up and grab it. We only care about the 2s and the 2p right now. These orbitals, like I've drawn down here, kind of overlap each other. We've got electrons sitting in each one. This inner one is the 1s. This outer one is the 2s. Then we've got 2p's hanging out all around it. These kind of even out that charge when we've got an atomic orbital. But this is not stable. Because it's not stable, as soon as this bumps into another fluorine, it is going to change so that it can bond with that fluorine and become stable. When these orbitals change, we call it hybridization, because these orbitals will merge together and make a hybrid orbital that's really a mixture of both of them. And so when our 2s and our 2p, all of them combine, we get our sp3, sorry, I wrote sp, this should be sp3 hybridized orbitals. What this means is that I've got one s orbital and 3 p orbitals all merging together. We can also have sp2 hybridized orbitals, where one s and 2 of the p orbitals will hang out. And we can have sp hybridized, where it's just one s and one p. But whenever we have something like this, where it's just going to form a single bond, we're going to have an sp3 hybridized orbital. We'll look at when we're going to have the other types later. For now, all of the stuff in the second set of orbitals, the n equals 2 orbitals, will merge together to hybridize. When that happens, these orbital shapes adjust. So where it was all of these funky orbitals kind of mashed together, now we're going to form very clear, separate places and we've got one that's kind of going to the back. So imagine that this one right here, is going into the page. Imagine that this one is coming out of the page. So this sets up a structure more like this. Okay? And so now my electrons are in these hybridized orbitals. I've got 2 in 3 of them and 1 in the 4th one. So let's put electrons in there. So I've got 2 electrons hanging out here, 2 here, 2 here, and 1 here. Okay? So when I say hybridization, what I mean is that these clouds of electrons, these spaces that electrons were normally hanging out in, merged together to form new spaces. It's like buying a house that has a bunch of rooms that are all put in weird spots, tearing out the walls and making new rooms where things will fit better. That's what this is like. Okay? This fluorine does that because it's in the presence of an atom it wants to bond with. It's doing that in response to the other fluorine atom. So let's draw that fluorine atom in here. This is our red fluorine. This red fluorine is going to do the same thing. It is going to bond. It's going to hybridize its orbitals in order to bond. So it's got sp3 hybridization, where the p and the s merged together. I've got one empty spot. There we go. So these merged together to form a very similar structure. When we talk about VSEPR diagrams, we'll talk more about this hybridization, what these angles are between these, what these shapes look like. But for now, all we care about is that it happens. So I call this a hybridized orbital. I call it sp3 just to give it a name. to give a name to this specific structure, this specific arrangement. When this arrangement occurs, this electron and this electron are able to then overlap. And so I get fluorine bonded to fluorine with this overlap of their electron orbitals. And so now I have specific regions in space around these atoms where the electrons are hanging out. So now each region has 2 electrons. And so it's got this negative charge. These are negative charges all around this. So all of these negative charges are pushing away at each other to make sure we stay in this exact same shape. There might be some variance, a little bit of vibration back and forth, but these regions of electrons, where the electrons are hanging out, they're hanging out in these clouds around the atoms, they're going to stay in those general locations to keep this charge evened out. When an electron tries to move out of that, it gets pushed back by this electron cloud, and these repulse each other, and this kind of pushes back into this spot. When it tries to go this way, it's repulsed by this guy, and it gets pushed back into place. And so my total electron cloud, my total hybridization, is really going to look like this. Got my fluorine here. I've got my 4 orbitals, my sp3 orbitals, all of my blue electrons in place. Let's move this down a little bit. Then my red fluorine is going to overlap. And so now one of these clouds of electrons has overlapped. And so when I have just one of these overlapping, it's going to form a sigma bond. So this bond right here, this overlapping of either an s orbital or an sp3 hybridized orbital is going to be a sigma bond. So this right here, sigma. Now, even though it's sp, it's still going to be an overlapping of this s orbital, this lowest energy possible. So we call this a sigma bond in line with s, so that we can recognize that, yeah, the s and the sigma are both the lowest energy bond states. This is going to be lower energy than the other type of bond we can have. Speaking of, that's what we're going to look at next.